Hi guys, welcome back from spring break. I hope you're all staying safe and staying healthy. I miss you all so very much. I hope you were at least able to relax a little bit during spring break and are ready for learning more algebra. Today we are moving on to our next unit, which is logs. Before we start talking about logs, we're going to talk about something that's you have been hearing a lot of in the news lately, and it is exponential functions. I know that in reference to the coronavirus, everyone's been saying, oh, it's growing exponentially, or they're showing you these exponential growth charts. And that's what we're going to be talking about today, exponential functions. So let's get started. We are Unit 15, Day 1, graphing exponential functions. And before we can talk about graphing exponential functions, let's just talk about what an exponential function is. It's basically a function where your variable is the exponent. So for example, we could have f of x is equal to b raised to the x power, where b will be a constant number and x will be the changing variable. Now, something we have to know about exponential functions is that b has to be greater than 0. And this is something really important to understand. Why? Why must b be greater than 0? Well, let's talk about what happens if b is less than 0. Let's think about it. Let's just pretend that b is equal to -2, which it's not allowed to be, but let's just say, what would happen? Well, if b was equal to -2, and if x was any integer, 1, 2, 3, it would work out, right? That would all work. But let's say that x was a fraction. For example, let's let x equal a half. So what would we have? We would have f of x is equal to -2 raised to the half power. Well, what's that? We know the half power is the same as saying the square root. Well, if f of x equals the root of -2, that would give us an imaginary number, and we don't want, or we don't graph imaginary numbers. So this is why b has to be greater than 0. B has to be greater than 0. So now, let's think about this. We know we're growing exponentially. What does it look like if you're growing exponentially? It means that you are growing at an insane rate. And usually the graph, as you've been seeing in the news, looks something like that. It is just growing so quick. Right? That's generally what an exponential function looks like. Right? But now we can increase, but we can also decrease, right? It can't only go up, it could also go down. Like that. So in what scenario is it increasing, and in what scenario is it decreasing? Well, let's think about that. If b is greater than 1, the function will be increasing. Hey, why am I saying greater than 1? Why am I not saying less than 1? I'm sorry, equal to 1, greater than or equal to 1. I'm saying b has to be greater than 1. Well, what if it were equal to 1? Say we had f of x is equal to b to the x power. And let's say we had b is equal to 1. Then it would be f of x is equal to 1 raised to the x power. But think about it. 1 raised to any power is just going to give us 1. So that's not an exponential growth. That's just a horizontal line right at 1. Right? So that's not showing any type of exponential growth. So what happens when b is greater than 1? So let's think of a scenario. Let's say that I have f of x is equal to 2 raised to the x power. Now let's go to our calculators and enter that in. So I'm going to have 2 raised to the x power. And there is our exponential growth. Okay. I want you to notice that it is hovering over the x-axis but never crossing it, which is huge. It's hovering over the x-axis but never crossing it. And I also want you to realize that we have it crossing the y-axis at the point 0, 1. Okay. I know that we saw this graph, but I still want us to plot it out ourselves. So let's go back to our notebooks and graph this out ourselves. So let's come up with some coordinates. So I'm going to pick some x and pick some y, figure out some y coordinates. So my x coordinates will be -2 first. So we're going to have 2 raised to the -2nd power, which is going to be 1 over 2 to the 2nd power, which is 1/4. Then I will choose -1, and we're going to have 2 to the -1st power, which is really 1 over 2 to the 1st power, which is 1/2. I'm going to, if you notice, I'm just increasing by 1 unit. I'm going to go to 0. We're going to have 2 to the 0 power, which is going to be 1. We're going to have 1, which is 2 to the 1st power, which is 2. And I will stop at x is equal to 2, which is 2 to the 2nd power, and we know that is 4. So let's plot these points. I'm going to have the point -2, 1/4, so over -2 up 1/4. I'm just sort of guesstimating where that 4th will be. We're going to have -1 to 1/2 there. We're going to have 0, 1, which we saw on the calculator. We're going to have 1, 2. We're going to have 2, 4. And if you notice, we're already starting that exponential growth. Now, my question for you is, can 2 to the x power ever equal 0? Can 2 to the x power ever equal 0? Ultimately, what I'm saying is, are we ever going to touch that x-axis? Are we ever going to have an x-intercept? And the answer to that is no, it's impossible. There's no value for x that will make it 0. Even when we put in 0, right, 2 to the 0 power, that's 1. We will never get 0. So that is why we're going to get an asymptote at the x-axis. So we are basically hugging it, but never crossing it. We are going to hug it, but never cross it. We get really, really close, but never cross it. Okay, so this is increasing. So when b is greater than 1, we're going to be increasing. Let's talk about your favorite things, domain and range. What is the domain of this function? The domain is going to be, remember, our x's. So what's the furthest left? What's the furthest left we go? Looks like -infinity. What's the furthest right we go? positive infinity. Okay, let's talk about our range. Now, the range will not be the infinities. What is the lowest point here? The lowest point is 0, but we're not really touching it. So that's why I'm going to do a round bracket for 0, and our highest point will be infinity. Okay, so that's an increasing function. Let's see, when would it be decreasing? I'm just going to erase this up. So when would our exponential growth be decreasing? It's going to be decreasing when our value of b is between 0 and 1. So when our value of b is between 0 and 1. Let's go back to our calculators and see what that looks like. Let's take a value for b between 0 and 1. I'm going to choose a half. So let's go through and enter this in. So I'm going to put parentheses, then 1 divided by 2. That's my base of b, and I'm going to raise it to the x power. And now we're going to hit graph. And if you notice, we have our exponential growth, but this time it's not really a growth, right? It's going down. So now we're decreasing, and if you notice, we have something very similar, just in a different direction. We are still hugging the x-axis. So once again, we're not crossing that x-axis. That x-axis is going to acting as an asymptote to us. And also, we are crossing the y-axis at that point, 0, 1. Okay, I know that we just looked at the graph, but I want us to go ahead and sketch this out just for fun. So let's go through. What did I do? So what did I say I was using? I was using the graph y equals a half raised to the x power. So I'm going to use the same values for x I used in the previous problem. So let's start off with -2. So I'm going to have a half raised to the -2nd power. Well, what's that going to be? That's just going to be 2 to the 2nd power, which is 4. We're going to have -1. So we have a half raised to the -1st power, which is just a half. I'm sorry, which is just 2. -1st power, we're switching it. We're going to have 0. Once again, anything raised to the 0 power we know is 1. That's why we have that same y-intercept, because anything raised to that 0 power will always be 1, which gives us that point 0, 1. Let's go on to 1. So a half raised to the 1st power is just a half. And once again, we'll move on to 2. We'll have a half raised to the 2nd power, which is a 4. Now, question for you. Could a half raised to the x power ever equal 0? Is that possible? Once again, it is not possible. No matter what value we substitute in for x, it will never yield a 0. So that is why we have that asymptote. That is why we have that asymptote at the x-axis. All right, let's graph this up. So we have -2, 4. We have -1, 2. We have 0, 1. We have 1/2. And we have 2 and a 4. So once again, we know we're going to be hugging that x-axis, but never quite touching it. Okay, so now that we know when b is greater than 1, we're going to be increasing. When we're between 0 and 1, we're going to be decreasing. There's some vocabulary we want to talk about. Let me just get to a new page. Okay, let's talk about our key points. Okay, so our key point that we noticed in our increase and our decrease is going to be the point 0, 1. And that's going to be the crossing. We're going to cross the y-axis at the point 0, 1 for any parent graph, meaning as long as there aren't any shifts left or right, up or down, we will be crossing that axis, the y-axis, at the point 0, 1. And that's simply because anything raised to the 0 power is going to be 1. So we know that's a solid for any of these exponential functions, like I said, unless we are shifting left, right, up, or down, or if there's a number to be multiplied by that b. Those are some scenarios where the key point will not be 0, 1. But anything in the basic format of y equals b to the x power, that's what I call a parent function. Anything in that format, you will be crossing the 0, 1, and that will be your key point. There will also be a horizontal asymptote 1 unit below that key point. There'll also be a horizontal asymptote 1 unit below that key point. What do I mean? Well, let's go back to the previous page. Our key point was 0, 1. If we go 1 unit below it, what's 1 unit below 0, 1? That's the x-axis 0, 0 here. And if you notice, there's a horizontal asymptote 1 unit below that. And there will always be a horizontal asymptote 1 unit below the key point. And that's going to work, except if there's a number being multiplied by in front of the b. What do I mean by that? Well, let's just write this down first. So the key point is going to be 0, 1 for any parent function. And when I say parent function, I'm talking about this format. And then I said there's always going to be a horizontal asymptote 1 unit below the key point, except when the base is multiplied by a number. What do I mean by that? The base is being multiplied by a number. So let's look at the function y is equal to 2 times a half raised to the x power. And I want us to go to our calculators and enter that in. So if we're back at our calculators, we have y is equal to a half raised to the x power. And like we pointed out below, here's our key point, 0, 1. We have an asymptote right below, 1 unit below that key point, which is the x-axis. I'm going to go back and I'm going to show you 2 raised to the x power. Just to show you, once again, we have a parent function, we have a key point at 0, 1, we have an asymptote 1 unit below that. I could do a different one. Let's do 3 raised to the x power. Once again, we have our key point at 0, 1, we have our asymptote 1 unit below that. So now let's see what happens when I put the number in front. So we said we wanted y is equal to 2 times a half raised to the x power. So we're still at an exponential. Function. We're obviously decreasing because the b is between 0 and 1. So now let's look what's happening here. So we have our key point is now the point 0, 2, because we're not in a parent function anymore. We've now changed this around. And the asymptote is not 1 unit below it. The asymptote is now 2 units below it. So like I said, that the trick with the 0, 1 and the asymptote being 1 unit below it only works if we're dealing with a parent function. The asymptote will always be 1 unit below the key point, except if there's a number in front of the. So let's go ahead and talk about different translations now. Go back to my paper, erase this. Okay, so obviously not everything will be a parent function. So let's say we have y is equal to b raised to the x minus h plus k. And we are so familiar with the shifting. So the h will be the horizontal shift. And the k is going to be the vertical shift. Okay, so let's think of an example. Let's do a sketch for f of x is equal to 2 raised to the x minus 3 power. So what I'm going to do is I'm going to talk about the parent function first. That's what I want to look at first. So the parent function for 2 raised to the x minus 3 power is, let's write this down, parent function is going to be y is equal to 2 to the x power. And I'm just going to do a sketch. I'm not going to get any real points. The only thing I really need to know is that we have our key point at 0, 1, because any parent function is going to have a key point at 0, 1, and we're going to have an asymptote 1 unit below that. What else do we need to know? We also need to know that because our b is greater than 1, we're going to be increasing. So it's going to hug our x-axis and then go up. Like I said, this is a sketch. I didn't actually find any coordinates other than that 0, 1. But now what is it telling us to do? It's telling us to take our parent function and we're shifting it. So this is in the format of 2 to the x minus h. So that means we're shifting 3 units to the right. So I'm going to take that key point, 1, and I'm going to shift it 1, 2, 3 units to the right. Now, just for a little bit of accuracy, if we wanted to, we can find the y-intercept. So remember, for the y-intercept, we let x equal 0. So we're going to have y is equal to the 2 raised to the 0 minus 3 power. So that's going to be y to the negative, 2 to the negative 3rd power, which is 1/8. So that's the point 0, 1/8. So that's going to be pretty low here. So once again, what's happening? We are hugging that x-axis and then spiking up. Okay, now that was a vertical shift. What happens? Let's erase this. What happens? That was a horizontal shift. I'm sorry, that was a horizontal shift. What happens with the vertical shift? The same idea. So let's go and graph f of x is equal to 2 to the x and then minus 1. Okay, so this time what are we doing? We're going to shift 1 unit down. So I'm going to think of my parent function. My parent function is f of x is equal to 2 to the x. Well, what does that mean? That means I'm going to have a turning point at 0, 1, and I'm going to have an asymptote 1 unit below that. So what are we going to do? We're going to take, not the turning point, that key point. We're going to take that key point, and now I'm going to shift it 1 unit down. So now my key point is the point 0, 0. And what does that mean for my asymptote? That means my asymptote has to be 1 unit below that. So instead of my exponential growth hugging the x-axis, now it's hugging the line y equals -1. And then going up. So now let's think of the domain and range for this. So I think we're clear the domains will still be the infinities, but now the range is going to change. Because now we're not hugging the x-axis, we're not hugging 0 anymore. Now we're hugging -1, and it's not touching it, so that's why it's a round bracket, and then we are going to infinity. Okay, what about if I gave you y is equal to b to the -x power? Well, I hope that you would just realize this is the same as saying y is equal to 1 over b to the x power. And vice versa, if I gave you y is equal to, in parentheses, 1 over b, close our parentheses, raised to the -x power, that is the same as y is equal to b to the x.